This is Chemical Processes for Micro and Nanofabrication. I'm Chris Mack, and this is Lecture 28, Device Interconnect Part 1 of a two-part series of lectures on the topic of how we connect our transistors together to create circuits. Our reading is Chapter 15 of our textbook by Campbell. Interconnecting the transistors is an extremely important part of the fabrication of a transistor. Up until now, we've been focusing mostly on how to make the transistor itself. We've talked about, for example, in the last lectures, device isolation. We've talked about the source and drain implants and what the gates are made of, etc. The transistor formation encompasses about half of the manufacturing process. And all of the steps of the CMOS process up to and including the formation of a completed transistor, we call that the front end of the line, or front end of line process, FEOL. Then, from the point when we've got working transistors to having a finished chip, that is all of the interconnections and finishing up of the device, we call that the back end of the line. And in the early days of integrated circuits, the front end of the line was the dominant, the most important part of making a chip. If you did a good job of making a transistor, wiring them up was pretty easy. But as the number of transistors has grown from a few thousand to a few billion, it's become harder and harder to connect all these transistors together. And in fact, the performance of the interconnect now is almost as critical to the overall performance, maybe even more critical to the overall performance of the device as the performance of the individual transistors. And that wasn't always the case, but it has become the case now. So we need to really think about the interconnect side of things, the back end of the line, in terms of how good our overall chip will perform, just as much as we think about the front end of the line, the transistors. When we looked at a CMOS process before, we thought about making the source and the drain and the gate, and then creating contacts and metal connections to the source and the drain and the gate, the three components. So we have, for example, a diffusion region, which we then cross with our gate, polysilicon gate. We do the implant, self-aligned implant that creates a source and drain on either side. Then we come in with a contact hole through a silicon dioxide and put metallization on top of that contact hole and make a connection. So I can make connections to the gate, I can make connections to the source and the drain. And with these metallization connections, shown here in the light blue, we can connect one transistor to another. Here I show these two gates connected to each other with a metal line. And then maybe a source will connect to a drain, or etc. Well, that picture looks very simple when I just have a few transistors to connect together. But when I have lots of transistors to connect together, things get more complicated. Let's look at a little bit more closely at the way, a more reasonable, practical way in which we connect these things together. So here's a stick diagram version, which just makes the drawing a little bit easier, but it has all the characteristics of this layout. So this is a kind of a layout drawing where the rectangle width represents the actual width of the metal line, for example, or the actual width of the polysilicon line. Here in the stick diagram, we ignore things like how wide they actually are, but the topology is about right. That is, if I show a polysilicon line moving and turning and coming back, that's actually what it does. It's the right topology. So, how are we making our transistors? Well, first we have this diffusion area. So here I have the N diffusion shown in the yellow. And then a polysilicon line crosses that. Every time a polysilicon line crosses a diffusion, we get a transistor with a source and a drain on either side of it. Then I have the P diffusion here, so I can make an N-channel device by crossing the N diffusion region with polysilicon. I can make a p-channel device by having the poly cross the p diffusion. I've got a ground level of metal on the bottom and a power supply VDD, positive voltage metal up at the top. I show these a different color just because of their different application, but really that's going to be a metal line coming across there, delivering the power and delivering the ground. And then in the blue I have the metal interconnections connecting up the different parts of the transistors together. And then this set of transistors might perform some simple function. I have an input signal and I take an output signal here. So what are some characteristics of how this has been laid out? Well, first of all, you might notice that the transistors are sharing a diffusion region. This is very common. Not every transistor in the circuit will share a diffusion region, but a large number of the close by transistors might share one diffusion region. So we see automatically we have a source and a drain on either side of this transistor, source and the drain on either side of this transistor, and this source and this drain are automatically connected together. Right? Here I show two polysilicon gates with a source and a drain on either side. Well, what's this in between? Well, that's the source of one and the drain of the other. They're connected together, but they're not contacted. I don't always have to make a contact. I don't always need to make a contact to a source or a drain. Here the source and the drain are contacting each other for these two neighboring transistors. The other thing you might notice is that the polysilicon is being used as a local interconnect. So here I have a PMOS transistor. Over here I have an NMOS transistor. If I want those two gates to be connected together, I could run a metal line between them, or I could use the polysilicon itself as an interconnect. As long as the length of that interconnect is not so great, because you know polysilicon is not too high of a conductivity. So we have a fair amount of resistance along that line. But as long as the line length is short, we can use poly to do connections. And you see we've got a connection between this gate and this gate using the polysilicon here. We've got a connection between this gate and this gate, and between this gate and this gate. But notice also that I can connect this poly gate to a metal line as well, and I can have different metal lines connecting different poly, like here connected to here along this metal. I don't always want to use polysilicon for every connection if it gets too long. And then I have metal that makes connections between the pieces as well. Notice that I've got a set of transistors down here all in a row and a set of transistors up here, the NMOS transistors, all in a row. And what do I do in the middle? In the middle I have all the wiring, the connections between them. Well, let's look at that in a little bit more detail and think about more than one row, right? So we have multiple rows of PMOS and NMOS transistors, in fact quite a large number of rows of these things. And then along each row I'll have multiple transistors. The space in between where we're going to run our wires to make our connections, we call these runs of wires tracks. So a track is a space where I'm allowed to run a wire to make a connection. The more wires that I need to run and the more connections I need to make between transistors, the more width I have to allow to run these tracks. So here I show a 3-track wiring, but maybe that's not enough. Maybe I won't be able to run enough wires to make all the connections I need with only 3 tracks. Maybe I'll need 4 tracks or 5 tracks. Notice that there's going to be some breaks in these rows of transistors to allow for some vertical runs as well. Well, this is how we were wiring up our transistors for many, many years. But we began to run into problems. First of all, the more transistors we had on our chip, the more connections we need to make between the transistors, and that required more wiring tracks. The more wiring tracks we used, the more area that we used up in our circuit just for the wiring. So we were consuming silicon area not because we were building transistors on that silicon, but we just needed the space to run the wires. So it became to occupy more and more space, consume more and more of the real estate of our chip. But even worse than that, we started having serious topology problems when trying to connect up. Let's take a look at the idea of topology, how we run these wires. So suppose I have two transistors A and B, and I need to connect them together. Maybe the source of one to the drain of the other, or connect the two gates together, or something like that. So what do? I just run a wire from A to B. Fine. Now I have two other transistors, C and D, and I need to run a wire to connect them. But now I have a topology problem. I've got a wire in the way, so I have to go around. Okay, well, I can go around. It makes the wire a little bit longer than it would otherwise need to be, and that's not necessarily good, but okay, I can live with that. Now I have two more transistors, E and F. Well, now I have to do something like run around even longer to get around the wires that are in the way to connect them. And you can imagine this problem multiplying as I go more and more and more transistors. Thousands of transistors, then millions, then billions of transistors. When I have just a single level of metal, it becomes extremely difficult to figure out how to run all these wires without running into any conflicts. I can find myself completely trapped where I can't get a wire out of that region. Well, there's a solution, and the solution is multiple levels of metal. What if instead of having to go around this wire because I couldn't cross it without causing a short circuit, what if I could go up and over and then keep on my path? You can imagine a wire that stopped, and then a metal wire that went vertically up, and then on another level I had another metal wire, and then a contact hole or via hole coming back down with that metal to make a connection. So I would go across on the first level of metal, go up to a second level of metal, run across without touching and therefore not short-circuiting this connection from A to B, coming back down and continuing on my way and connecting to D. And now you can see, of course, the E to F wire is also shorter. So by using, in this case, just two levels of metal, I've been able to reduce the wire lengths of the C to D transition and the A to B connection. Well, this brings up a couple of other interesting points. The difficulty of making these connections from, say, C to D is a function of where the transistors C and D are. Where do you put those transistors in the first place? That problem, I've got a circuit diagram, I have a bunch of things that I have to connect in a certain way. Where do I physically place them on the silicon surface? That's called placement, or place. Where do I place the transistors? Then a connected problem, pardon the pun, is the routing. When I want to make a connection from C to D, and from A to B, or from E to F, where do I run the wires? The choices I make intersect each other, interact with each other. If I run the wire from A to B in a different direction, it changes the difficulty of running a wire from C to D. If, for example, on this single level of metallization, I were to realize I can move this transistor C up here, well, then I'd have no conflicts at all, and all of my metallizations would be as short as possible. The goal of place and route, placing the transistors and then routing the metal lines that connect them, the goal is twofold. One is I want to minimize the length of the wires connecting each transistor. and I want to minimize the area of the chip. Minimizing the length of the wires affects the performance of the chip. A shorter wire means the signal travels more quickly to get from point A to point B. And the area of the chip is simply economic. The smaller I can make the chip, the cheaper that chip will cost to make. How do I make the area of the chip smaller? Well, that's a function of how much extra space I use up to run these metal lines. If I have to make room to run a line and I have to spread my transistors out to give me room to run that line around, well, that uses up real estate and makes the cost of my chip go up. If, on the other hand, I can figure out where to place and route these lines so that they use less area, well, that results in a cost savings. Multiple levels of metal is one of the ways of reducing the length of these metal lines in the area of the chip, but also figuring out the optimum placement and the optimum routing of these lines contributes to the minimizing the area of the chip and the length of the wires as well. Well, I'm showing just 4 or 5 or 6, connections here possible, and it's pretty simple for you to look at this and say, oh, we just need to move the transistor C and we'll have a much more efficient place and route. But that's not as easy to figure out when there are thousands of transistors or millions of transistors or billions of transistors, and the complexity of figuring out where to place all 1 billion transistors and how to route the wires for the billions, more than a billion connections between them is a daunting task that requires some serious compute power to come up with even reasonable approximate answers for getting close to the minimum wire length and the minimum area of the chip. Multiple levels of metallization is one of the approaches that we use to optimize these trade-offs. We add more levels of metal and it shortens up the length and reduces the area of the chip. But each layer adds cost. 3 levels of metal, it costs more to make than 2 levels of metal. But these extra levels of metallization allow for a smaller chip area. That saves you money. Well, now we have a trade-off, and we can optimize the costs. The more transistors we have, the more metal layers we need. When we had 1 million transistors, we needed 3 or 4 levels of metal. When we had 10 million transistors, we needed 5 or 6 levels of metal. When we had 100 million transistors, we needed 7 or 8 levels of metal. And today we have 1 billion transistors, and state of the art is on the order of 10 layers of metal to make all the connections that we need to make. Here is a cross-section diagram and a 3D example plot of multiple levels of metal. Here it's a 5 metal layer. All of the metals are copper. Down here at the bottom we have the transistors, and we see what we call the front end of the line process up till about here. So here's the gate and the source and the drain to either side, and a STI device isolation between. Our connection to the source and drain is made with a tungsten plug. So we're going to cut a contact hole and fill it up with tungsten. We talked about that earlier. Remember that tungsten is deposited with CVD, and then we're going to polish it back off to make it flat. But then from then on, all of our metal lines are going to be copper. In the early days of single level metal, we used aluminum metallization, but for reasons we'll talk about in the next lecture, we now prefer copper as our metallization approach. So what do? We have a layer of metallization shown here, and then a contact from this layer down to the tungsten plugs through vias here. So in this case, the wires in this copper 1 metal, the metal 1 layer, the wires are going in and out of the page And we usually have all of our lines in one metal layer oriented pretty much in the same direction. That's the most common approach. Then up here we have a copper layer 2, and we show a line going back and forth, and it makes a connection to copper layer 1 by cutting through an insulator and making a contact. Then here's copper layer 3, here's a via down to copper layer 2, here's copper layer 4. Copper layer 4 is mostly in and out of the board, so you see the even copper layers are going in and out of the board, and the odd copper layers are going left and right. We can get some stacked vias. You see copper layer 4 through via to 3, through via to 2, through via straight down to the tungsten. So we have a direct connection from this copper line to this source of a transistor. And finally at the top we're going to have some connection to the outside world through the packaging. Here it's a solder bump that will then connect to a package which has a lead that comes out and connects to our world. Well, you can see that there's a lot of metal layers. This is just 5, and we have up to 10 today. It occupies a lot of the portion of the chip making process. In fact, we do more lithography steps and more deposition steps in the back end of the line in many processes today than we do in the front end of the line. So let's look at what we've learned so far in our brief introduction to the science of interconnection between our transistors. You should be able to define the front end of the line and the back end of the line. What do those two things mean? What are the goals of place and route? Define what place means, define what route means, and then tell me what the goals are. Why have we stopped using single layers of metal? What are the limits of using just a single level of metal? And what are the trade-offs of using more metal levels? If one isn't good and we want 2, well, won't 3 always be better than 2? Well, what's the trade-off? When do we reach the optimum level of the number of metal layers? Well, that's our introduction to Interconnect for our devices. Part 2 of Interconnect coming up next.